So what we're going to talk about today is solid phase peptide synthesis. Solid phase peptide synthesis, abbreviated just SPPS. Okay. Now, the purpose of this experiment is for you and I to synthesize peptides. In solid phase peptide synthesis, you're limited to how big the peptide can be. There's some limitations. And it's approximately, you could go from up to 50 to 60 amino acids on using this technique. But more, that's kind of really stretching it or pushing it. So the best size would be like in the 30 amino acid range is what solid phase peptide synthesis is good for. And so it's all to make a peptide. And then this whole thing right there, solid phase, what that means is you are going to generate, you're going to have a resin bead. Okay? We have a resin bead there. And that resin bead is just a polystyrene bead. And when you see it in real life, it just looks like a grain of sand, about that size. Okay, and on that resin bead, you're going to have something called a spacer. Okay, and we'll just put that in a little box right there. You're going to have a spacer, and then you're going to have a linker. All right. So there's a linker, and then attached to that linker, you're going to put your first amino acid. And now what you can do is attach a second amino acid to it, and then a third, all the way up to however big your peptide is. But you need this solid support system so that when you generate your peptide, it doesn't wash away in the solution. So what we do is we take a lot of these resin beads, stick a lot of these spacer and linkers all over. So these lines that I'm drawing here represent all of this, okay? And then we're going to take lots of those resin beads and stick it into a fritted cylinder here. So if we have a funnel system like this, right, like that. And then what we have right here is a frit. We have a frit that will allow solvent and solutions to go through and drip down here, okay? But the resin beads represent that. So here's all our resin beads. Okay. And so what's going to happen is when you add your first amino acid, it will attach to the resin bead. And then that amino acid needs to be washed away so you can add the second amino acid. Say if this amino acid is proline, and then this one is alanine, you have to get rid of all the proline before you add the alanine. And in order to do that, you have to wash it with organic solvents to get rid of all the proline. And then you add the alanine in. So that's why you need the frit, so the resin doesn't disappear, so we can keep track of it. But the solution that contained the amino acid is washed away when we don't want it anymore. Okay, so yes, you can stop this when you want the solution to stay in the frit or the syringe, or you open this up to let the solution out. So what we're doing is just adding amino acid onto this solid support until we get our peptide. So there's some things that we need to understand about the process and how this all works. So the first thing that you need to know if you want to make a peptide is the peptide sequence. So we always draw our peptide sequence from N terminus to C terminus. So let's just come up with a peptide here. Let's do a serine, threonine, serine. Okay, and then we will do, okay, so I'm just coming up with some random peptide here, okay? That's what I want to make. So that's the first thing that we need to make sure we get 100% correct is what is the peptide sequence. Because if you just swap the R and the D, then everything's messed up. It's not the same peptide. So that's kind of like where your OCD kicks in and you're like triple checking this, like, do we have this? And do we have it correct, okay? The second thing that you want to pay attention to is this terminus right here. The C terminus. You get to choose what that C terminus is. Now, a native peptide would have the carboxylic acid, right? It would have the carboxylic acid C terminus end. And if you want that, then you have to use certain resins. And one resin that will give you a C terminus is something called the Wang resin. Now you could, if you wanted to, for reasons that we won't discuss here, what if you wanted it to be a amide? All right, an amide. So that's kind of a little weird, but you can have a amide C terminus. And that one you would need a rink resin. Okay. And then there's also, you could also have a thioester. Okay. And in order to do thioesters, you would have to use a Dawson resin. Okay, but for my class, we are just going to focus our attention here on just the native peptides. So we want to use the Wang resin, so we get that C terminus end. Okay, so that's the second step. The third step, and let's put that right here. Okay. So the third step is that when you synthesize a peptide, you have to synthesize it in the direction of C to N, which means you have to synthesize it in this order. So the first amino acid that you're going to attach to the resin is aspartic acid. And then the next amino acid is serine. Okay? So like in your notebook, when you're doing the synthesis, you are writing it down. Typically, I write it like this: DSDRSTS. Make sure I know that's the N terminus. Make sure I know that's the C terminus, right? And then I keep track. And I double check this, DS, and make sure the sequence right. And so when I go to synthesize my peptide, I start here. And when that one's done, I do the next and just do a checklist. But that's the order that you're going to synthesize this peptide. Okay? Now, why do you have to synthesize it from C terminus to N terminus? And it all has to do with this idea of racemization. Okay. Okay. So racemization is when you form the peptide bond. Okay. So let me represent a peptide bond here. So this is just a generic one right here, okay? Now, what we want to have happen is the configuration of this side chain to be S or L, right? That's what it has to be if we're talking about a native, normal peptide. That has to be R. When you synthesize from C terminus to N terminus, we prevent racemization from happening. If you synthesize the peptide from N terminus to C terminus, then you're going to see a lot of racemization. And what that is that this stereocenter right here, okay, is now going to be racemized, which means you're going to have a mixture of L and D amino acids. And there is research, active research, where people make D peptides. But in this experiment that I'm talking about, we want the L, okay? We don't want a mixture. And so synthesizing it from N to C makes this, which then ruins your peptide. Okay, so that's the reason why we have to synthesize from C to N, is to prevent racemization. So step 4, what we need to be aware of is the type of solid phase peptide synthesis that we want to do. There's 2 versions out there, or 2 main ones. We have what's called an Fmoc solid phase peptide synthesis, okay, and Boc. Fmoc right here is going to be a base sensitive reaction, and Boc is going to be acid sensitive. Did I get it all on the screen? No, I didn't. Okay. And so for this video, I'm only going to worry about Fmoc synthesis. And Boc synthesis, I'm just going to not talk about that one, okay? So then, this was, in my opinion, the easiest one to use is the Fmoc, and I feel it's also the safest, for reasons we can talk about at a later date. Okay, so going to my peptide sequence, what was the amino acid that needed to be put on first? Aspartic acid, right? So I'm going to take that aspartic acid right here, and I'm going to kind of omit this part and just draw that so this rectangle right here, I'm just going to represent it with this little square, okay? So that square represents the resin, the spacer, and the linker. And attached to that, we have this aspartic acid. So it's going to look like this, okay? That's not what I wanted. Let's actually... let's draw it more like this. Okay, so we get our zigzag looking the way. And H2. Now, one thing to notice, okay, is when we draw peptides, we draw it from N to C, correct? So if this is our N terminus, we would have this guy here. Then we would have this. So let's draw ourselves a dipeptide. Like this, and then like that, okay? So that's from N to C, we have 2 amino acids. We notice that at the apex here, at this alpha carbon right there, what do we have? We have a wedged side chain. And then when the alpha carbon right there is apex down, we have the dash, right? Okay. So now we come here to our first amino acid. I'm at an apex. Why did I draw it with a dash? And the reason why I drew it on a dash is because I took this whole peptide and I flipped it 180 degrees. So when you read it from N to C, this is how you want it. Apex, wedge, apex down, dash. But now when we're doing solid phase peptide synthesis, it's been flipped around. Okay? So what you'll notice is that this configuration at that stereocenter is still L. It's just we flipped it around. Got to be aware of that, okay? So there's our aspartic acid. I'm not going to draw out the whole side chain there, okay? So we've attached our first amino acid. Now the next challenge is, what is the next amino acid? That's what we want to attach. All right? So if we do that, and what was the next amino acid in my peptide? I believe it was a serine. All right? So we have a serine amino acid that we want to put on there. And so what does serine look like? So we want to add serine, so we have, there's our amino acid, there's the amino acid serine, okay? So what we want to have happen now is we want this lone pair on the amide nitrogen there, okay? Amine nitrogen. We want it to come in here and form the amide bond. So at the end of the day, what we want after this second reaction here, what we want it to look like is this. So that's aspartic acid, and then we want it to form it with down, up, let's see here. So that would be that. And that's our serine side chain. And then we would have what? Our alpha amine. So if we count, look at this. This nitrogen right here is this guy. And that nitrogen formed a bond with this carbon, which is that carbon. And there's the site, the alpha carbon, and now this amine right here, or that nitrogen atom is now right there. All right? So that's what we want to have happen. Okay? But there's a problem here. A big problem. Can you see what conflict could happen here? This is kind of like wishful thinking. We have this on the resin. We're going to take this amino acid, okay, and we're going to put it into a vial and have a solution. We will take in our syringe here with our frit, we have our resin beads. What we're going to do now is take that solution of serine, which is this guy right here, and we're going to dump it in. We're going to stop this so it doesn't leak out, and we're going to let it react. If we do that, we want this amine to attack this carboxylic acid. All right? But what's preventing this amine from attacking another serine? So if we draw another serine like this, because there's going to be a whole lot of serines, right? We have a solution of it. So if that's our first serine, that's our second one. What's preventing this nitrogen from attacking that carboxylic acid? See, we want this one to attack just that one, but we're in a solution. This is going to do some attacking. And it's just going to be a complete mess. What if you have a side chain that has lone pairs? Now that can go and attack. And it's just a lot of reactions that can happen all at the same time. And so what we want to do is control the reaction, okay? And so the way that we control that is by using a protecting group, and that was the Fmoc part, okay? So what we're going to do is protect this amino acid right here. To prevent these other reactions that I'm talking about, what we're going to do is buy an amino acid, okay, that has this alpha amine right here protected with Fmoc. And so what that means is that this nitrogen isn't active. It's not going to be able to react. So in this reaction scheme, this plus this, only this alpha amine will react because this alpha amine is protected. Okay? And so what Fmoc right there is what? Fmoc, remember, is base sensitive. Okay? That's going to be important in a minute. Okay? And then I also mentioned that the side chain right here, some side chains can also react. So what we need to do to that side chain, is to protect it as well. And in this particular case, serine is protected with a tert-butyl group. Okay? But the side chains, so we say side chains, protecting groups, those have to be acid sensitive. Okay? So I'm just setting this up and then we'll put it all together, okay? So we have Fmoc, base sensitive, a protecting group. It's not always going to be a tert-butoxide piece. Depending on the side chain, it could be different protecting groups. But what you need to remember is the side chain is protected with an acid-sensitive protecting group. Okay? And so if we come back to this side chain right here, let's put a little P right there to represent that it's protected with an acid-sensitive group. This this nitrogen has no Fmoc on it, so it's the one that's going to react. Okay? So the protecting groups solves the problem of all these side reactions that we don't want to have happen. Okay? Now there's another problem here that we need to be aware of. Okay? And that is if you go back to organic chemistry and ask this question, can a amine react with a carboxylic acid? And can it react efficiently, forming this peptide bond right here? Can it form, that's not the peptide bond, sorry, this one. There's the peptide bond right there. There's the amide bond. Can it form that bond with relative ease? Amine plus carboxylic acid. And if you remember and think about that, you'll be like, no, that does not happen very well. And so what we have to do is in this solution right here, when we put our amino acid in there and dissolve it in an organic solvent, we need to do a reaction just in this flask right here. Okay? And what we need to do in this flask, which has serine in it, so we have this serine with the Fmoc on it and the acid-sensitive side chain protected. This whole amino acid is going to go into this organic solvent. And then what we're going to do is convert this carboxylic acid into an ester. Okay? We'll change that to an ester. And now if you go back to organic chemistry and say, hey, do amines react with esters to form amide bonds? And you'll be like, yes, they do. So what is the reagent that we added to this solution? I'll tell you the ingredients, but I don't need you guys to worry too much about what they are. other than I'm just going to share with you what the ingredients or the reagents are, but you don't need to stress out about remembering those too much, okay? So you have to add DIEA, okay? So the diisopropyl ethylamine, that's just a weak base, okay? Then we have HBTU and HOBT. And the solvent that we're going to use is DMF, is typically the solvent that you use. So adding all that to the amino acid, it will convert the carboxylic acid into a ester. Okay? Now, if you want to know what that ester looks like, then we could talk about that in office hours. Okay? So that solves some of those problems now that I've highlighted. All right? So what are those? What did we just, to summarize real quick, Fmoc protecting group, side chain protecting group, converting the carboxylic acid into a ester with these reagents right here. We do that reaction in here, and then we add it to the resin. And what does the resin have on it? This piece. And then that nitrogen is going to react with that carbon or this ester group to form this bond right here. Okay? Okay, now when you do that reaction, let's pay very close attention. This nitrogen right here is that nitrogen. So it's missing what's going on here. We have our hydrogen and we have our Fmoc. The Fmoc is still there, and this side chain, which is this one, is protected. Okay? Now, how do we, now we have 2 amino acids on our peptide, or on the resin. How do we add a 3rd amino acid? Well, this nitrogen right here can't react with any esters. Okay? So what we have to do is after we do this reaction and we form this dipeptide, we're going to drain it, drain all the DMF. So this solution, we're going to drain it. Then we're going to wash the resin beads with just pure DMF. So we're washing off all the serine reaction. Once it's thoroughly washed, then we'll cap it off again. Okay? And then we're going to add a deprotecting reaction. And what we're going to do is we're going to deprotect the Fmoc. Okay? We want to rip off the Fmoc so this nitrogen can do another reaction. Let's back up a little bit. So doing this reaction in the flat or in this reaction vessel and then adding it to the resin beads to add the amino acid, that's called a coupling. So that's our coupling reaction when you add an amino acid on. So you do a coupling. After you do a coupling reaction, your amino acid looks like this. It still has Fmoc on it. After you do the wash, you will then do a deprotection. So a deprotection step is removing the Fmoc. And the way that we remove the Fmoc is just with reagents called piperidine. Piperidine and DMF. Okay? And that's just a base. And piperidine looks like this. It's a 6-membered heterocycle. Okay? Just like that. So it has some lone pairs right there. So this amine right here is going to do a reaction in which it takes Fmoc off. So after deprotection, we're going to have, let's say, the deprotection solution in here now. Okay, we add it in. We let the reaction go. After the reaction's done, we let it drain. And so all the deprotection solution now drains out. Then we wash it again. Make sure all the deprotection solution is gone. And after that's nice and clean, our peptide is going to look like this. It's going to add that hydrogen back. Beautiful. So now we have our free amine to do the next reaction. And what did my peptide sequence say the next amino acid is? It was a D, so aspartic acid. So we do the same steps all over again. We get a reaction vessel. Instead of serine, we put aspartic acid in. We add in the DIEA, HBTU, HLBT, DMF, make that reaction happen. We add it to the resin beads, and then we just rinse and repeat, and do this over and over and over and over again until we come up with our peptide. Okay? Once we've synthesized our peptide, there's one last thing that we have to do, and that is to get it chopped off of the resin. We have to and we have to get rid of all the protecting groups that are on the side chains. Now, let's make a distinction here. The deprotection of the Fmoc was done with piperidine, which is a base. Okay? But to remove the protecting groups on the side chains and to cut it off from the resin, you just have to add some acid and a few other chemicals. So the major chemical that you have to add is TFA. Let's just put it right here. So TFA, standing for trifluoroacetic acid. Okay? So it's basically a really souped up, powerful vinegar. Yeah. Okay, so we get some TFA and we add some other reagents. We call them scavengers. Okay. So some of the scavengers that we use is phenols and EDT. So these are just supposed to scavenger up any side reactions that we don't want to happen when we rip off these protecting groups, okay? So the main thing that I want you to remember is that, hey, if we want to remove protecting groups and cleave it from resin, we have to add acid, which is trifluoroacetic acid. And so we take that trifluoroacetic acid and add it to our resin if it's been washed and clean, okay? Before we cleave, we call it cleaving the peptide from the resin. Before we can cleave the peptide, we need to make sure these resin beads have been washed thoroughly, that there's no coupling solution, there's no deprotection solution. Once that's been washed, we add our TFA and we let it stir. And then we open it up and our peptide, the solution, TFA is a liquid, that's going to drip out. And what we're going to do is collect that solution in ether. And when that solution hits the ether, very, very cold ether, your peptide precipitates. And so you see this nice white substance that's just going to form as a solid. And then you filter it off and gather your peptide. And that's how you generate a peptide by solid phase synthesis. And then from here, you will go to the purification techniques. So you would go to, if you want to learn about how to purify a peptide, you would look at HPLC purification with the reverse phase chromatography. And I have videos about that if you're interested in learning about that, you can watch those. But that's solid phase peptide synthesis in a nutshell. One thing that I want you to be aware of is that when you go to the textbook to read up on solid phase peptide synthesis, there's going to be some differences. And one of those differences is the coupling reagents. So these are the coupling reagents that I personally use when I've made peptides, but your textbook is going to show other reagents. So I don't want you to focus so much on what are these reagents. More, I want you to understand those are coupling reagents. These are piperdine's deprotection and things like that. Okay, so I don't want you to get confused if you're reading the book. But if you have any questions or concerns, please reach out. I'll be happy to help.